autonomous equation, differential equation, and stability. Suppose here a first order differential equation dx dt equal to fx. Here fx is a function of t also, x is a function of t also, x is a function of xt also. If in the right hand side t is the time present explicitly, then this system is called the non-autonomous system. And if in the right hand side t is absent, then it is non-autonomous system, sorry, autonomous system. So first consider this is differential equation, first order. Obviously this is first order differential equation, and maybe linear or non-linear. Here x is the dependent variable, and t is the independent variable, dependent variable. Now what is the equilibrium point? An equilibrium point or critical point or singular point is a point x star such that f of x star is equal to 0, and other points are called regular point. So in this expression 1, if fx star equal to 0, right hand side is fx star equal to 0, that is dx dt equal to 0. So dx dt is equal to 0. Solving this, you get the singular equilibrium point or singular point, critical point. X is equal to x star is also a solution of the above differential equation 1, and this solution is said to be an equilibrium solution of the differential equation. Now some definitions: asymptotically stable, unstable, and so on. The equilibrium solution x is equal to x star of the differential equation 1 is said to be asymptotically stable if there exists a neighborhood of x star, say n star, nx star, such that the solution to 1 with starting value x0 is equal to at x suffix 0 belongs to the neighborhood n of x star will have the property xt tending to x star as t tends to infinity. So t is the time increases. When time increases, then xt tends to x star. X star is a fixed value. This x star, this fixed value is determined by this equation fx star equal to 0 from the given differential equation. So when xt is any value of x any x will, tends to x star, this is a critical point as t tends to time increases. Intuitively speaking, stability means a solution starting nearby equilibrium point which always converge to equilibrium. And unstable, the equilibrium solution x is equal to x star is said to be unstable if there exists a neighborhood x star, say nx star, such that the solution to 1 differential equation 1 with starting value x0 at the point t is equal to 0 is equal to x suffix 0 belongs to the neighborhood of x star, this n, capital N, nx star, will diverge away from x star as t tends to infinity. When time increases, then x diverge away from x star. Then we say that this solution is unstable solution. Semi-stable, the equilibrium solution x is equal to x star is said to be semi-stable if the solution to the differential equation 1 with starting the value, initial value x at the point 0 time t is equal to 0 is equal to x0 will diverge away from x star when x0 greater than x star, or on the other side x0 less than x star, and converge for the other side to x star when if x0 greater than x star for away, and then x for converge x to x star when x0 less than x star, or alternatively this. Intuitively speaking, semi-stability means one-sided stability. Note that this is for essential for the computation of the problem. if f dash derivative with respect to time t, derivative this f dash x star at greater than 0, then x is equal to x star is unstable equation, equilibrium solution, and fx changes from a negative sign to positive sign as age x increases across x star, and arrows on the two sides of x star are moving away from x star. If f dash x star is less than 0, then uh, then x is equal to x star is asymptotically stable equilibrium solution, and fx changes from positive sign to negative sign as x increases across x star, and arrows on the two sides of x star are moving towards x star. And if f dash x star equal to 0, then and if double dash x star not is equal to 0, then the equilibrium solution x is equal to x star is semi-stable, and fx does not change sign as x increases across x star. So we go to some example, then clear this idea. To clear this idea, this is the first order differential equation. Obviously x is the dependent variable here, x square, so it is a nonlinear differential first order differential equation. This is a nonlinear first order differential equation, and so to find the stability of the solution, actually here in the right hand side, this right hand side is called, this is called fx, and here t not here explicitly in the right hand side. So this is a autonomous system, first order difference. Obviously it is nonlinear due to the term x square, nonlinear first order differential equation. So to find the equilibrium point x star, f x star is equal to 0, that is dx dt is equal to 0. So solving this, put this x star square minus x star minus 6 is equal to 0, and solving this we get x star equal to minus 2 and x star is equal to 3. So here x star equal to minus 2 and x star equal to 3 are two equilibrium solutions, equilibrium points of the differential equation 1. Note that this is also solution of the differential equation 1, this equation 1. So so if you try to solve this differential equation, then you get this this type of curve, if you draw say if you draw a solution for this differential equation, try to solve this differential equation, try to solve this differential equation, you get the solution curve is this type. So initial condition, if initial condition is this, say x at the time, this is the time axis, this is the time axis, and this is the x axis. Suppose x at the time 0, is equal to 3. So this is the x at the time 0 is equal to 3. So this is the, if this is the initial condition, then the solution curve is going to this way. This is the solution curve. When t increases, t tends to infinity, then x in this direction, going to the direction this. You get a particular curve this. So you get the particular curve in this particular curve with the initial condition this. So you can easily determine from the given differential equation this, you get the, with the initial condition x equal to 3, you get the particular curve, solution curve is this. If you get the other initial condition, you get other solution curve. So and this is the solution curve, and this this xt space, totally filled by the solution curve. But when x equal to 3 put in the differential equation, so and this is the solution of the differential equation. Put the x equal to 3 on the left hand side and right side and get the solution this. So this solution is this solution, x is equal to 3, and this is the solution curve. So this is the solution curve, and this away from this. So from this curve x equal to minus x equal to 3, this is the straight line, this is equal to x equal to 3. So this is the solution curve is moving away from the line x equal to 3 solution curve. And if this line is x equal to -2, this -2, this line -2, obviously x is equal to -2 is also a solution, equilibrium solution of this of the given differential equation. And here notice, observe that the solution curve moving towards the line x is equal to -2, x equal to -2 with time increases, and this is the time increases. This is the solution curve. This is the solution curve. The solution curve. So here x is equal to -2 and x equal to -3. So all solution curve, all solutions going to x is equal to -2, and here all solution, if you starting from this point, then this point, so this point, so solution with time t, solution going to the line x is equal to -2 with time increases. And if you starting this point, this point, so your solution curve going to the x equal to -2. So here x equal to -2 plays a role of attractor. Uh, so so this is the sketch of the integral curve, solution curves of the directional fields, but it is difficult to draw for a nonlinear differential equation to find the solution, to draw this solution curve. So first you solve this, but it is difficult in the real field, so we avoid this and simply the sketch phase portrait. To sketch it appears that the solution that the near start near x is equal to -2 is an asymptotically stable. Here notice that x is equal to -2, the solution curve is asymptotically stable, but solutions that start near x is equal to 3, solution start near x is equal to 3, this curve all move away from it at time t increases. So x equal to 3 is unstable equilibrium solution. This is the unstable equilibrium solution. So in the practical field, first you draw, so this avoid this calculation when discuss about the critical point in examination. So start from this. So here draw the line x-axis, this is x-axis, and this is the line dx dt, and so here dx dt equal to x square minus x minus 6. So this is called fx. So so this line is fx, so the fx is equal to this, f equal to this. So plot the draw the graph of x square minus x minus 6. So this is my factor x minus 3 and x plus 2, and so x equal to 3, cut the x-axis, this graph, and x equal to -2, cut the y-axis. So here this 3 is unstable and x is equal to -2 is stable solution. This is called phase portrait of the solution. Here find f dash x with respect to x, derivative with respect to x, not t, fx. So here f is equal to this x square minus x minus 6. So here fx, so find f dash x. So f dash x equal to this 2x minus 1. So find the f dash at the equilibrium and critical point -2. This is equal to -5, that less than 0. This is less than 0. So by the theorem, this when f derivative at the point -2 is negative, so is a stable equilibrium solution x equal to, so this start attract to the point -2. Here note that in this case when f dash x star is less than negative, then x is equal to x star is asymptotically stable equilibrium solution, and fx changes from positive to negative as x increases. Fx changes from positive to negative here from as x increases. Here at the point near -2, at the point fx is equal to this this line. So this is positive, fx is equal to positive. This line, this is the positive axis. Along the positive axis, this is positive. So when x along the x increases, this point fx is downwards. So this is negative. So fx changes from positive to negative across this point, and f dash x is negative. F dash x is negative. So this is the stable equilibrium, and in this case, so we draw the arrow in this direction towards -2. This is the point stable equilibrium. Actually, here we draw from the integral solution is this. When t-axis and x-axis, these all trajectories is going to the line x is equal to -2. So this is x is equal to -2 is an attractor. So this is the attractor. So this is the one dimension is this towards the solution towards -2. And for 3 x equal to 3, so find f dash 3 put here 2x minus 1. So this is equal to 5, and f dash 3 is greater than 0. So when derivative is greater than 0, that means derivative is greater than 0, that means x is increasing, derivative is negative, so x is monotonically decreasing. So x is monotonically decreasing, and in this here x is monotonically increasing for when f dash equal to 3. So when f dash equal to 3 greater than 0, so from this note, when f dash 3 greater than 0, then is unstable solution, and fx changes from minus to plus sign, and arrows on the two sides of x star are moving away from x star. So here x star, so from x here in these sides, left hand side of 3 is the negative sign, because here fx is downwards, and here right hand side of 3 fx is positive, since fx is upwards. So when across 3 as x increases, fx changes sign from minus to plus, since here derivative f dash x is positive, so x is monotonically increasing. So in this case the unstable, and so we put here arrow away from the point 3. This is unstable, away from the point 3 is unstable, and actually in this figure the all solution trajectory is away from the line x equal to 3. If you draw the solution trajectory in the xt space, so all trajectories away from the line x is equal to 3, and this is the phase portrait. In the phase portrait we draw this, we put here away two arrows from the point 3 going away from the point 3, and when going away from the 3 in this called is unstable point, And next example, consider the system dx is equal to minus x plus x cube. Find the equilibrium points and draw phase portrait and discuss the stability. Here dx is equal to this, so obviously this is a autonomous system, because in the right hand side এইটা আমরা অ্যাকচুয়ালি এই সলিউশনটা সবসময় এই সলিউশন স্পেসটা আমরা বার করতে পারবো না, এটা খুব অসুবিধা আমাদের পক্ষে, এটা আমরা বার করতে পারছি না। এর সলিউশনটা বার করতে গেলে খুব ক্রিটিক্যাল হয়ে যাবে, এটা খুব সহজ না, এটা নিয়ে বার করতে পারবে সবসময়, এটা পারবে না তুমি বার করতে। এই সলিউশন কার্ভগুলো বার করা খুব ডিফিকাল্ট যদি নন লিনিয়ার ইকুয়েশন হয়ে যায়। নন লিনিয়ার ইকুয়েশনের ক্লোজড ফর্মে সলিউশনগুলো বার করা, সলিউশন মানেটা কি হবে, এর সলিউশনটা বার করলে তোমার এটা এরকম ধরনের একটা সলিউশন আসবে। এই যদি সলিউশনটা বার করো, x is equal to some c1 into some e to the power something plus c2 plus some c1 একটাই আসবে কনস্ট্যান্ট, e to the power something, এরকম ধরনের একটা ফর্ম আসবে, এবং এটা বার করা খুব ডিফিকাল্ট নন লিনিয়ার সলিউশনের ক্ষেত্রে। এবং সেখান থেকে এই সলিউশন থেকে x is equal to t এই ফর্ম থেকে তুমি সলিউশন কার্ভগুলো ড্র করবে, যদি তুমি এই পার্টিকুলার এই ইনিশিয়াল কন্ডিশনগুলো পাও। যদি ইনিশিয়াল কন্ডিশন x is equal to x0 equal to 3 তোমার দিয়ে দেওয়া থাকে, তাহলে তুমি এই একটা কার্ভ মাত্র ড্র করতে পারবে, এই একটা কার্ভ তুমি ড্র করতে পারবে। এখানে আমরা ইন্টারেস্টেড যে তার সলিউশনের নেচারটা কিরকম হবে। অর্থাৎ এখানে এক্স ইজিক্যাল টু সলিউশনটার নেচারটা কীরকম হবে, তোমরা নেট সার্চ করলেই দেখতে পাবে যে তোমার ওই ডিরেকশনাল ডেরিভেটিভ বা এই জিনিসগুলো দেখতে পাবে। তো এখানে সলিউশনের নেচারটা তোমরা একটা কার্ভ, এবং এখানে আমরা অ্যাকচুয়াল সলিউশনের নেচারটা জানতে চাইছি, হ্যাঁ, বা ফেজ পোর্ট্রেটের সাহায্যে, যে এখানে 3 ডাইমেনশনাল স্পেস কিন্তু নয়, তুমি একটা জায়গায় ভুল করছো, এখানে 3 ডাইমেনশনাল স্পেস কিন্তু নয়, এটা সবই কিন্তু 2 ডাইমেনশনাল স্পেসেই হচ্ছে, সব এখানে এক্স টি এগুলো সব 2 ডাইমেনশনাল স্পেসে আছে। যদি যদি আমরা এরকম ধরনের সলিউশনগুলো বার করতে পারতাম, সব সলিউশনগুলো যদি আমরা বার করতে পারতাম, যদি এখানে এরকম ধরনের অনেক আছে ম্যাথ ডিফারেন্সিয়াল ইকুয়েশন সলভার আছে, সাহায্যে আমরা এই টি অ্যাক্সিস আর এক্স অ্যাক্সিস পুট করে দিয়ে আমরা যে সলিউশন কার্ভগুলো বার করতে পারতাম, তাহলে সলিউশন কার্ভগুলো তোমার এরকম ধরনের সলিউশন কার্ভ তুমি বিভিন্ন কার্ভ জেনারেট করতে পারতে, এবং এই পুরো স্পেসটা এই সলিউশন কার্ভ দিয়ে ফিল হয়ে যেত। এবং এই অ্যারোগুলো দেওয়া হচ্ছে কেন না, এই টি টাইম বাড়ার সঙ্গে সঙ্গে, টি ইজ টাইম, হ্যাঁ, টাইম বাড়ার সঙ্গে সঙ্গে এক্সটা তোমার এই দিকে দিকে বেড়ে যাচ্ছে। তুমি এখানে টাইম টি ইজিক্যাল টু 1, এখানে টি ইজিক্যাল, এই যে টি ইজিক্যাল টু, ধরো এটা টি ইজিক্যাল টু 1, তুমি এই কার্ভটা যদি মুভ করো, এই কার্ভটা তুমি করো টি ইজিক্যাল টু 1 পয়েন্টে, যদি এই ইনিশিয়াল কন্ডিশন দিয়ে স্টার্ট করো, তাহলে টি ইজিক্যাল টু 1 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানে, টি ইজিক্যাল টু 2 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানটায়, টি ইজিক্যাল টু 3 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানে, টি ইজিক্যাল টু 4 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানে, টি ইজিক্যাল টু 5 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানে, টি ইজিক্যাল টু 7 পয়েন্টে এক্স এর ভ্যালুটা হবে এখানে, যদি এই ইনিশিয়াল কন্ডিশন থেকে স্টার্ট করো ইনিশিয়াল কার্ভটা দিয়ে। কিন্তু আমাদের এখানে এই সম্ভব নয় এই সবসময় এই সলিউশনটা বার করা, সবসময় বার করা। তো যদি আমরা এইভাবে ইকুইলিব্রিয়াম পয়েন্টটা বার করে নেব, ইকুইলিব্রিয়াম পয়েন্টগুলো সেপারেটলি সলিউশন of the differential equation, and this is non-linear first order differential equation is also solution. Equilibrium points are also solutions of the first order linear differential. If you put x is equal to 3, is satisfied. If put is equal to x equal to -2, is also satisfied. So actually by this phase portrait we trace the nature of the solution curve. So if you start from the region from -2 to 3, suppose here start initial solution x0 start from this point, x0 start from, so x at the point t is equal to 0 is called x0, this is the initial condition. So if x0 is this here, x0, suppose x is equal to 1, so suppose x at the point 0 is equal to 1, so then you see that the solution trajectory this going to this point x is equal to -2. So see this figure, so x is equal to x0 is equal to 1, so x0 means time t is equal to 0, x0 is equal to 1, so x0 is equal to 1 is this, so x0 is equal to 1 is this point, this is equal to x0 is equal to 1, x0 is equal to 1. So starting from this point, so you get the solution trajectory in this way, and this solution with time t increases, this solution trajectory going to this way and going towards x is equal to -2. So in the phase portrait, if you start the initial condition x0 between here -2 to 3, within the -2 to 3, then solution trajectory goes to the point -2. If x0 starting this point, so suppose here x0 is this, initial condition is this, x0 equal to 4, then the solution trajectory away from the point x is equal to 3. By this figure, so by this figure, this suppose x0 is equal to 4, suppose x0 equal to 4, here t is equal to 0, so x0 means this 0, x0 equal to 4, so suppose this is x0 equal to 4, this is x0 equal to 4, so if you start the initial condition with x0 is equal to 4, x0 equal to 4, then you get the solution curve in this way, so this solution curve moving away from the line x is equal to 3. So x is equal to 3 is unstable here, and here x is equal to -2 is stable here, and this is the phase portrait for this. And next consider this example from this, and dx dt is equal to 0, and solve this. X0 is equal to, we get this x0 here. Obviously notice that this here the term, due to the presence of the term x cube, this is a nonlinear equation, so it is difficult to solve the closed form of this sum x is equal to solve this x is equal to something is equal to in explicit form, x is equal to some expression of t is equal to this. some g of t. This is the solution of this. So for this nonlinear equation, we find these equilibrium points by f x star equal to 0 and get 3 points x0 is equal to 0, minus 1, 1. So we draw the x-axis, and this is the x dash. This is equal to, this line is the y-axis is the dx dt, dx dt. Dx dt actually means the velocity. If x is the position with time t, and dx dt means the velocity. This is the x is the position and dx dt means the velocity. So draw the graph minus x cube, minus x plus x cube. Draw the graph. So draw this graph minus x plus x cube by the demos. Sorry. This is the graphic calculator by the website demos. So plot here demos is equal to conic section, polar form, polar equation, Cartesian equation, y is equal to y equal to x square, x here the is this minus x plus x cube, sorry, minus x plus x cube. So minus x plus x cube. So this is the figure. So this is the x-axis, this is the corresponding y-axis. That means here the y dash dx dt is the y-axis, and point 1 intersecting point 0 intersecting point with the x-axis is the minus 1, 0. So this is 3 points are the corresponding equilibrium points. So 1, 0 and minus 1 equilibrium points, minus x plus x cube for this. So here my 1, 0 and this is not a solution curve. This is not a solution curve. This is just here this is the dx dt is equal to minus x plus x cube. So find these equilibrium points is this, and these equilibrium points is also solution of the given differential nonlinear first order differential equation, and dx dt is equal to this. If x is x 0 less than x0 less than 1, if this point 0 less than x0 less than 1, then x dot means this is the x dot is equal to this. So this is called fx, x dot equal to 0. So x0 square minus 1. So x dot is less than 0. X dot is less than 0. So if x0 lies between 0 and 1, so this x dot is less than 0. You can find another way by finding the derivative of this fx. So find the f dash x. Fx is equal to minus x plus x cube. So f dash x equal to minus 1 plus 3x square. This minus 1 plus 3x square. So from this point, so put here x equal to minus 1, x x1 star equal to minus 1. So put f dash minus 1. This equal to minus 1 plus 3 into minus 1 square is minus 1, that is equal to 3 plus 1 2. So f dash is positive, so this is positive, f dash is positive, minus 1. So f dash is positive, and this point from fx is negative, below downwards, and here in the right hand side is fx is positive, negative to positive, and so negative to positive, and f dash x is greater than 0. F dash is greater than 0 means the x is monotonically increasing function. So here -1 is unstable, and hence put the arrows -1 away from -1, two arrows away from -1, and hence since -1 is unstable. And then f dash at the point 0, f dash at the point 0, from this 0, this is the -1, this is -1, so this is less than 0. So less than 0 means here, so left hand side of 0 is positive, right hand side 0 is negative. So this function x is monotonically decreasing, so decreasing. So for this decreasing, so here x is equal to 0 is stable, by the theorem. So stable means put two arrows towards O, is stable. And last point, f dash at the point 1, f dash at the point 1 is equal to -1 plus 3. So this is equal to 2, greater than 0. So x is here monotonically increasing, and this is the unstable. So this one point is unstable, point 1, x is equal to 1 is unstable, and so put here two arrows away from the point 1. So if you start the initial condition x0 at the point x is equal to, at the point 0 is equal to x0, if x0 lies between 0 and 1, suppose x0 is here, lies between 0 and 1, then the solution trajectory is going towards the point O. If x0 starting initial point is starting from this point, this region, right hand side of 1, x0 is here, then the solution trajectory going away from the x is equal to 1. So here 1 is unstable point, 0 is stable equilibrium point, and -1 is also unstable equilibrium point. This is the H portrait. Next differential equation, dx dt is equal to x square minus 1. So the equilibrium points, solving this, x square minus 1 is equal to 0, x1 star is equal to -1, x2 star is equal to +1, and H portrait, we draw the H portrait. So x square equal to 1, this is the x-axis, the dx dt. So y is equal to x square minus 1, put this, and here -1 and +1. So find f dash, find f dash, this is called f. So f dash is equal to f dash x equal to 2x. So when f dash equal to 2x, f dash equal to 2x, so f dash at the point -1 equal to, at the point -1 equal to 2 into -1, that is equal to -2, less than 0. So this less than 0, so here x is monotonically decreasing. So monotonically decreasing, here this downwards from the point -1, left hand side x is positive and right hand side x is negative, dx dt negative. So this -1 is the point is asymptotically stable equilibrium point. So put the arrows towards the origin. So f dash is negative, is the point is stable, and f dash 1, critical point, f dash 1 is equal to 2 into x, so 2 into x, 2 into 1, that is equal to 2, positive. So obviously x is equal to 1 is unstable. So put the arrows from away from the point 1. So if you start some initial condition with x0 at the point here, then the solution trajectory is going away from the point 1, x is equal to 1. Consider the following initial value problem: dx is equal to ax plus ax minus b. Here a is non-zero, b is constant. Find the equilibrium point and discuss stability. Here for critical point dx is equal to 0. So from this x is equal to b by a. So only one critical point x is equal to b by a. The solution of the given differential equation is xt is equal to x0 minus b by a e to the power at plus b by a. And we solve this equation dx is equal to x plus minus b. So xt is equal to solved by this equation. So here the details of the steps here done here is done here, and so this is the xt is the solution of this, and b by a is the x star critical point. So b by a is the x star critical point. If x0 initial point is equal to x initial starting point is x star, then xt is equal to x star. If you put x0 is equal to x star, so this is equal to 0, so x is equal to x star. So obviously x star is also a solution of this equation. Now if a, this constant a is negative, so this e to the power minus t, a is negative, so this t increases, t tends to infinity, this term is going to 0, so xt tends to x star. So if a less than 0, then the solution xt going to x star and as t tends to infinity. However, if a is positive, so if a is positive, so this term going to infinity as t tends to infinity, so xt is going to infinity. So this is the when the a less than 0, the solution will converge to the equilibrium point x is equal to x star is equal to b by a. So this is the x star is equal to b by a is stable if a is less than 0 and unstable if a is greater than 0. And for this, if suppose here dx is equal to ax minus b, so here suppose here a is equal to x dot is equal to dx dt is equal to ax minus b. So put here a is equal to minus 2 and b is equal to 3. Suppose here a is equal to minus 2, b is equal to 3 in this case. Then this x star is equal to b by a. So this is equal to minus 3 by 2. So this is the point. This is the point, and this is the f is equal to here. F is equal to minus 2. F dash is equal to this is the f. F is equal to this. This is equal to f. So f dash is equal to minus 2. F dash is equal to this less than 0. This less than 0. This is less than 0, and so this is the point x is equal to minus 3 by 2 is stable point, equilibrium point. And other solution x dot is equal to 2x minus 3. So here a is equal to 2 and b equal to 3. The y is equal to x minus 3, this equation. So x star equilibrium point b by a, so this is equal to 3 by 2, and this f dash x is positive, so f dash is positive, so x is equal to 3 by 2 is unstable. Discuss the stability of the ODE dx is equal to fx, where fx is equal to x into x minus 1 minus x minus beta, where 0 less than beta less than 1. For equilibrium point, fx is equal to 0, so x is equal to 0, beta 1, where beta lies between 0 and 1. Equilibrium point is this. So find f dash x. So f dash x, find the derivative of f dash with respect to x. So this, so put f dash x at the point x star is equal to x star 1. So x star 1 equal to 0. So f dash this is equal to 0. So this 0, second term 0, third term 0, and from the first term, when x1 star 0, so put 0, 0. So this is equal to minus beta. Obviously beta lies between 0 and 1. So obviously minus beta is negative. So f dash at the point x1 star negative. So this is the x1 star is equal to 0 is equal to stable. And f dash x2 star, here x2 star equal to beta. So x2 star equal to beta, put this, so this beta, this third term 0, this first term 0. So from the second term, beta in 1 minus beta. So obviously this positive quantity, because beta lies between 0 and 1, so f dash is positive quantity. So x2 star beta is unstable. And third case, when f dash x3 star means 1, so from 1, second term, first term 0 because 1 minus x, and second term is also 0 due to the presence of 1 minus x. So only from third term put x is equal to 1, so minus 1 into 1 minus beta, so this is minus 1 minus beta. So beta lies between 0 and 1, so this obviously positive quantity, and this negative sign, so this negative sign. So f dash 1 is less than 0, so x3 star equal to 1 is stable equilibrium point. So if you draw this graph for this x into 1 minus x into x minus beta, so draw this type of graph, and from this phase portrait is 1, this beta and 0, and beta is the unstable, 0 is the stable, 1 is the stable. So draw the two arrows towards the point 1, and beta is unstable, so draw the two arrows away from the beta, and obviously note that 0 is also stable, so arrows going to the point 0. Obviously when x0 lies between 0 and x0 lies between 0 and beta, suppose here x0 is this. So suppose x0 is this point, initial point x0. So when start with initial point from this point 0 and beta x0 lies between this, so the solution trajectory going to the point 0, x is equal to 0. So limit xt t tends to 0 is equal to 0 from this figure. And if x0 is greater than beta, suppose here x0 is lies greater than beta and less than 1, then for this initial solution x0 at the point time t is equal to 0, then solution trajectory is going to the point x is equal to 1, going x to the point 1, limit xt tends to t tends to 1. So 1 is stable and 0 is stable, but beta point is unstable. Consider the following Gompertz model of population growth and find the stability, discuss the stability of this Gompertz model of the population growth. Dxt is equal to rx log k by x, and the initial condition x at the time t is equal to 0 is equal to x0 greater than 0, and r and k are positive constant. So dxt is equal to fx, so here fx is equal to rx ln k by x log to the base e. So fx is equal to this, since r is positive, so from this relation 0, so from this relation this, if you put x is equal to x star is equal to k, then k by k log 1 is 0, so only the equilibrium point is the unique equilibrium point, x star is equal to k, unique equilibrium point. And from this if we divide by x, 1 by x dx dt is equal to r ln k by x, and this ddt of ln x equal to ln k minus r ln x from this relation, and transform the variable, this x variable, put u is equal to ln x, so from this relation you get du dt is equal to this, and from this relation ddt equal to this, so adjustment the term, we get ddt of u e to the power rt is equal to r e to the power rt into ln k. Integrating this, we get the this plus c integrating constant using the initial condition u0 is equal to ln x0, that is equal to ln x sub x0, then from c is equal to ln x0 minus ln k, and so from this equation put the value of c, we get this relation u e to the power rt is e to the power rt ln k plus ln 0 x0 minus ln k, and from this u is equal to ln x is equal to ln k plus ln x0 by k e to the power minus rt. Now This is the solution of this. If t tends to infinity, so e to the power rt tends to 0. So this term is 0. So ln x tends to ln k. That is xt tends to k as t tends to infinity. So here kxt is equal to k is stable equilibrium solution of the given differential equation. But if r is negative constant and k is positive, then from this last equation r is negative, so this negative and negative, so positive, so this term is going to infinity. So this k x is equal x star is equal to k is unstable equilibrium for this. So this completes this lecture. Have any question? Hello? হ্যাঁ বলো, হ্যাঁ বলো, শুনতে পাচ্ছি, বলো। মোহন দুয়ারি, দাঁড়াও, মোহন দুয়ারি, হ্যাঁ দিয়েছি। আর কেউ? নাম বলো। সাইকেল নাজিন, হ্যাঁ। আর কেউ? আমি বললে হবে না, নামটা বলো, নামটা বলবে তো। বিশ্বই, আমি গলাটা বুঝতে পারিনি। বিশ্বই, ঠিক আছে। আর কেউ? মহাদেব মিটিয়া, মহাদেব মিটিয়া, মহাদেব মিটিয়া, মহাদেব মিটিয়া, হ্যাঁ। আর